So last time when we met at that time, that was on 16th February, I had started the second part of catalytic reforming, which is an extension of the first part in terms of how we actually convert that chemistry of catalytic reforming into a technology, and from there onwards into a kind of operating plant. So, if you recall, I had talked about the reactor configuration, which is a typical three reactor configuration. So, I'll quickly recap what we discussed last time, and then we will actually go on from where we stopped last time. So any catalytic reforming unit is a typical three or a four reactor configuration where the feed along with the recycled hydrogen passes through these three reactors. And since the reaction is endothermic, each time we go through a reactor, we have to preheat the feed. Sometimes there is even a four reactor configuration, but today, and in fact, even in the last 10, 15 years, most of the reformers are actually a three reactor configuration. And actually, as you already know, the major reaction is transformation of naphthenes to aromatics, that is the dehydrogenation. So that is highly endothermic, and so there is a big temperature drop in the first reactor. Then we actually preheat the feed again. So that actually goes then into the second reactor where actually the rest of the dehydrogenation takes place. And the other reactions start happening. That means the dehydrocyclization of paraffins as well as isomerization reactions. And that also creates endothermicity, a drop in temperature. So we preheat the feed once more and we pass it through the third reactor. So if you look at the profile of the three types, that is the naphthenes, paraffins, and aromatics, right across the three reactors, you will see paraffins keep on reducing as you go towards the third reactor. The naphthenes almost disappear, while actually both of them get converted to aromatics. So at the exit, the aromatic concentration is pretty high. Now, if you look at the catalyst distribution in the first, second, third reactor, from these reactors, you can visualize that we actually put less catalyst. In the second reactor, we put more catalyst, and the largest amount of catalyst is in the third reactor because we need more residence time for those difficult reactions like isomerization of naphtha, cyclopentanes to cyclohexanes, as well as dehydrocyclization of paraffins. The first reactor mostly does, dehydrogenation of naphthenes to aromatics, which is pretty fast reaction. So as we go along, the distribution of the catalyst is also in the same way that if suppose I put a total of 100 tons of the catalyst in the three reactors, 10 to 15% is in the first reactor. Roughly about 15 to 20% is in the third reactor, and the rest in the last reactor. In this case, of course, this is a four reactor configuration. But if there is no four reactors, then you can just add up and then divide by 100 and normalize and calculate like what will be the percentage in each of these reactors. And the reason is, of course, the rate of reaction. So we went through all that. And also we discussed like why the sizes are different. One more thing which I should mention is that if you look at these furnaces, the furnaces are in the reverse order. In other words, the largest furnace is right in the feed because we have to provide the entire heat right up to 520, 530 degrees Celsius for the reaction to happen in the first reactor. And then, of course, we just have to give a small amount of heat to go from this temperature to this temperature. So basically, the duty required in the H2 is much lower as compared to the duty required in H1. And then actually the temperature drop is still lower. So basically in H2, we have to go from this temperature to this temperature, while in H3, we have to go from this temperature to this temperature. So unlike R1, R2, R3, where R1 is the smallest and R3 is the largest, H1, H2, H3 is the reverse. That means H1 is the largest and H3 is the smallest in terms of furnace duty. So the sizes of the furnaces is also reduced from H1 to H2 to H3, while the reactor volume goes up from R1 to R2 to R3. And that is because of the relative endothermicity of the various reactions that you see in this table. And the size of the reactors is basically because of the rate of reaction and the various reactions that take place. We have gone through all that. And then after that, we discussed the various operating variables that are important in terms of both the product yield as well as the product quality. In this case, the product quality is more in terms of octane or the aromatics content in the product. So there are four important variables: reaction temperature, space velocity, reaction pressure, and hydrogen to hydrocarbon mole ratio. So these are the four important variables. And other than that, feed quality is something that is not in the hands of the operator. That depends upon the crude. If it is naphthenic crude, it's supposed to be a better feed for reforming because the N plus 2A becomes higher. And the catalyst type, of course, catalyst once loaded, it lasts for 5 years before you change. If you look at from an operational point of view, there are only four variables. Here again, uh, the operator doesn't have much play in terms of the reaction pressure and space velocity because the space velocity is more or less decided by the throughput. If you put higher, throughput, the space velocity comes down and so on and so forth. So we went through all that. In fact, reaction temperature is something which is in the hands of the operator. And here we actually consider as a weighted average inlet temperature, which is a kind of a sum average of inlet temperature in all the reactors multiplied by the weight of the catalyst. And similarly, we can have a weighted average bed temperature. So we discussed all this. And then I told you how the reactor temperature affects the concentration of aromatics or the octane of the product. It is very sensitive. For every 3 degrees rise in the reactor temperature, you can increase the octane by one number. And this is typical of most of the reformers. So this is one handle which the operator has. But of course, this is also within the limit of the furnace duties that you have. As far as space velocity is concerned, again here, the lesser the space velocity, the more is the severity of reforming. So the higher the temperature, more is the severity of reforming. Space velocity is the other way around. If you increase the space velocity, the residence time goes down, and therefore actually the severity of reaction comes down too. So both have similar impact actually. But if the operator wants to go up on space velocity, and again space velocity is determined by two variables. One is the liquid hourly space velocity, that is the total volumetric flow in liquid volume of the feed upon the volume of the catalyst, or weighted hourly space velocity, which is weight of the total weight that is tons per hour of the reactor charge upon the tons of the catalyst which is there. So that is, and typically we operate in 1 to 3 range depending upon the temperature at which you operate. So basically, if you go up on throughput in any reforming unit, the operator has to increase the temperature also to compensate for the lower residence time or a higher LHSV. Similarly, we talked about the pressure is, of course, one of the most important variables, and it has a historic perspective because when catalytic reforming was invented, the pressures were of the order of 70 bar. And because of developments not only in the catalyst but also in the technology, in terms of continuous regeneration, the pressures have been reduced down to what we know about is 3.5. And the pressure actually has immense effect on the coking of the catalyst. If you reduce the pressure in the operation, then there is more coke deposition on the catalyst because higher pressure actually promotes hydrocracking. And hydrocracking reduces the reformant yield, but it decreases the coking of the catalyst. Typically, if you want to have a longer cycle life, before regenerating the catalyst, we should typically operate at a higher pressure, because not only the hydrogen partial pressure goes up, but also actually it helps to do hydrocracking, which actually reduces the coke formation on the catalyst. So pressure is very important to reduce the coke formation, and therefore a longer cycle life before two regenerations. So this is very clear. I mean, the idea is to actually operate at lowest pressure as possible, but we are limited in terms of the coke deposit on the catalyst, and therefore the regeneration cycle. So with new technologies, which I'm going to talk about now, like the continuous catalyst regeneration technology, there actually, since we are regenerating the catalyst continuously, we can afford to go down on pressure. So you can see that when you go down on pressure, the yields go up, or for the same yield, the octane goes up. So if you're looking at almost like 80% yield, for 30 bar the octane is less, for 10 bar, the octane goes up. So basically, either way, the total amount of octane barrels goes up when you go down on pressure, which is beneficial. And this shows you actually this particular table, that when you go up on pressure, go down on pressure, the total amount of C5, that means the reformate, yields go up. 83 to 90% yield is significantly higher for a certain octane severity of 100. The fourth variable is the hydrogen to hydrocarbon ratio, that is the recycle. Moles of hydrogen in recycled gas upon moles of hydrocarbon. The main purpose of the hydrogen recycle is to increase the hydrogen partial pressure in the reaction. And here, actually, the phenomena is the same. If we have a higher recycle, to that extent, the severity is lower and the coke deposits is lower. Because actually, the more you put hydrogen along with the feed, any coke deposit on the catalyst, actually hydrogen reacts with those coke precursors or even the carbon deposit on the catalyst, and clears out the surface. So when you want to go for higher severity, generally people go for less recycle ratio. That means lower hydrogen to hydrocarbon ratio. So keep that in mind, that if you, and this is one handle in the hands of the operator. If you also increase the hydrogen to hydrocarbon ratio, the space velocity also goes up, and therefore the residence time goes down, and therefore actually you actually get less reformate, and the same phenomena as we discussed earlier. What are the advantages of reduction in hydrogen to hydrocarbon ratio? Idea is that we normally should operate the unit at lowest hydrogen to hydrocarbon ratio, uh, limited by the carbon deposit on the catalyst, and limited by the regeneration cycle that we are looking for. And so the advantage of that is that because we are recycling less, so we are putting less duty in the compressor. So we save energy costs in running the compressor. And the second is that it favors naphthalene dehydrogenation, because remember, this was an equilibrium reaction. So the less hydrogen you put along with the feed, the more actually the reaction will go towards the right. The disadvantage, of course, is because any reduction in hydrogen to hydrocarbon ratio leads to carbon increase. And the table here, if you recall, I had discussed this earlier also, that it's almost like 2 times higher if you go from 4 to 2, or from 8 to 4. As far as feed quality is concerned, we have had a lot of discussion about that earlier. Basically, the lighter feeds do not have either naphthenes or aromatics, so they are poor feeds for reforming. But the heavier fractions actually make a lot of sense, because not only they have aromatics, but there's significant quantity of naphthenes. Both are good in terms of N+2A. And this graph actually tells you that why naphthenic feed is preferred, because for the same octane, you get a better yield, or in terms of octane barrels, you get a higher octane barrel if you have more naphthenes. And we discussed this table actually why we prefer a certain fraction with respect to the ultimate product that we would like to make. coming now to the refining, to the reforming processes as such, which are the basic technologies that I wanted to talk about. There are basically in the entire world only two types of catalytic reformers which operate today, even in our own country. One is called the semi-regenerative reformer. It is called SR reformer in short, and we will talk about it in great detail. And when we discuss semi-regenerative reforming, you will understand why and how the pressure and hydrogen to hydrocarbon ratio plays a vital role in trying to operate a unit like a semi-regenerative reforming. So here, why it is called semi-regenerative? Because actually the reforming process operates almost for 10 months to almost like 14 months, where the catalyst goes through a gradual deactivation, and then we shut the unit down for regeneration. So it's a kind of a semi-regenerative. In other words, it is the unit operates almost for a year, and the catalyst slowly degrades. And then once we know that it is no more economically viable to operate this unit, we shut it down and then we regenerate. We just burn off the coke from the catalyst, and then the catalyst is ready to go to come back again for operation. I don't think I'd like to discuss cyclic because this was something which was invented by ExxonMobil, but it's ultimately not used anymore. The only idea here was what ExxonMobil did was, in addition, they added one more reactor to an SR reformer, so that while the reformer is still operating, they actually take one reactor offline and regenerate that catalyst, and then we then take that online. So idea is that if you have four reactors, out of which three reactors are in operation, you can always switch off one reactor and then regenerate that catalyst. But there are several issues linked with that, and so basically this technology got very quickly into a disuse. The second is, of course, what we operate today, and any new modern reformer, either being built today or actually being operated today, is actually a moving board bed, or what we call as a continuous catalyst regeneration unit, or CCR. And CCR, what happens is that we actually can, it is not a fixed bed unit. The semi-regenerative reformer is a fixed bed. What I mean by the fixed bed is actually that the catalyst is actually loaded in the reactor and it stays there. And then after 5 years, we remove the catalyst and fill new catalyst. And we regenerate the catalyst in situ. While the catalyst is sitting in the reactor, we regenerate the catalyst. While in the moving bed or continuous catalyst regeneration unit, the catalyst moves continuously through the reactors, and ultimately it is withdrawn from the last reactor. And typically these are three reactors, so it goes from the first reactor to the second reactor to the third reactor, and then it is withdrawn from the third reactor and it is regenerated and passed back to the first reactor as a fresh catalyst. So, we can now you can understand that what is the basic difference and why actually the industry invented CCR. Because in semi-regenerative reforming, you lose a lot of yield and advantages of operating at low pressure. SR reformer, you cannot operate at low pressure because otherwise the catalyst will get deactivated within 2-3 months, and then it is not cost viable to shut down the unit after 3 months and regenerate the catalyst. So let me actually explain what is the difference in the operating conditions between the semi-regenerative reformer and the moving bed CCR. I'm not going to talk about cyclic because they are no longer in use. Semi-regenerative reformer, the catalyst is basically bimetallic catalyst, but it is in the form of an extrudate. That means जैसे हम सेवई खाते हैं ना, it is that long noodles type thing, about 1.5 millimeter diameter, 2 or 3 millimeter long. So these are like what we call as extrudates. None of these semi-regenerative reformers operate less than 25 bar, 25 kg per square centimeter. With the monometallic, with the bimetallic, we could reduce it down to 15 bar, but no less than 15. The semi-regenerative reformers that we have operating in India, none of them operate less than 15 to 16 bar. We generally keep a higher hydrogen to hydrocarbon ratio. And now you can understand why pressure and hydrogen to hydrocarbon ratio are so important in terms of creating a long life of the catalyst before regeneration. Because in semi-regenerative reforming, we cannot we continue the operation for 1 year and then stop the unit and regenerate. So for 1 year, the unit is operating. But what happens is that since the catalyst is deactivated slowly, what we do is that we increase the reactor temperature from the beginning till the end. So there are two conditions, what is called SOR and EOR, start of run and end of run. So when you have the fresh catalyst and you start operating the unit, it is called start of run. So in our industry, we have this is typical for any fixed bed, technology, and we'll talk about hydrotracking and other things later. So in any fixed bed technology where actually the catalyst gets slowly deactivated, there is a terminology called start of run and end of run. So in semi-regenerative reforming, at start of run temperatures are much lower as compared to end of run. The reason is that actually the catalyst gets deactivated. So in order to compensate for the deactivation, the operator increases the temperature. So just to give you an idea, suppose at start of run we start at 510 degrees Celsius. At end of run we might end up at 530 degree or somewhere around that, so that we compensate for the deactivated catalyst. But then beyond that, it becomes uneconomical, or we might hit the temperature limits of the metallurgy of the unit. If you compare this with the moving bed CCR, again, of course, it is bimetallic. There's no monometallic catalyst here, and as compared to semi-regenerative reforming, if you recall, in part one, I talked about that in semi-regenerative reforming, you use platinum rhenium as a catalyst, while here it is platinum tin. And unlike SR reformer, where we use extrudate, here these are spheres, very tiny balls, something like 1 to 1.52 millimeter diameter. And the white is in spheres, in spheroids, because it helps to actually move the catalyst from the top to the bottom. If you make it extrudate, the extrudate will not be able to move because they are like a long noodle type of structure. So we need spherical balls so that the movement is easy. And the pressure is very low, you can see. Roughly any new CCR, see our CCR that we have in Jamnagar, in Reliance, they were constructed way back in 99, 2000, 2001 time frame. At least the one that is in the old refinery. And so there the operating pressure is about 8.5 bar. The new CCR reformers which are coming up would be around about 3.5 bar. Why we can actually afford to reduce the pressure as well as reduce the hydrogen to hydrocarbon ratio? Because we don't care whether the coke lay down on the catalyst has, because we are actually regenerating that catalyst continuously. So any coke laid on the catalyst is of no concern because we are handling that on a continuous basis. So we can also actually see that because of that, our octane is high, yields are also high. So in CISA reforming, you make much larger amount of octane barrels. And this is significant difference, 19 to 92 compared to 100 to 102. Uh, of course, there's another thing which I would like to talk about in terms of the differences between the SR type of reformer and CCR type of reformer. So one major difference, so there are several differences between SR reformer and CCR reformer. One difference, of course, is that in a SR reformer, the catalyst bed is fixed, while in CCR reformer, it is a moving bed. In SR reformer, the catalyst is like an extrudate, while in CCR it is spheres or tiny spheres. In its bimetallic catalyst in SR is platinum rhenium, while here it is platinum tin, and the pressures are a lot lower, and the hydrogen to hydrocarbon ratios are much lower, and you get much higher yield. So let's talk briefly about semi-regenerative reformer. This is where actually I had stopped. I remember last time. If I'm looking my notes, yeah, we actually stopped here. So this was just a recap, so that because of the long gap, I took some more time to go through the recap, so that I don't lose you while we are discussing the rest of the part two. So if you look at the semi-regenerative catalytic reformer, this is how actually the technology got invented to begin with. And these reformers are still around. In fact, one of these reformers was actually installed in Numaligarh refinery even in 2006, 2007 timeframe. And I'll tell you why. Why did it not go to CCR? So semi-regenerative reforming, this is process is characterized by continuous operations over long period with essentially decreasing catalyst activity. Okay. So it is the unit is in a dynamic mode, in the sense that right from start of run to end of run, and I have defined what is start of run and end of run. Right from start of run to end of run, the catalyst goes through a gradual degradation, and we essentially try to operate the unit at a higher pressure and a higher hydrogen to hydrocarbon ratio. So we actually, decrease the activity of the catalyst, and that way actually we have to suffer in terms of yield of aromatics and the purity of the hydrogen recycle. Um, so in order to maintain the conversion nearly constant, the reaction temperature is raised. So as you go from SOR to EOR, as I said, about 15 to 20 degrees rise in temperature happens. And when you actually reach the end of the cycle, where actually it is no more economically viable to run the unit, we shut down the unit and then regenerate the catalyst in situ. And we'll talk about catalyst regeneration together, both for SR and CCR reformers. The shutdown of this unit occurs approximately once about a year. I think I haven't seen these reformers shutting down in 6 months. It's roughly about 12 to 14 months. 14 months at the most. 14 months is almost like a stretch target. And this is the range in which we actually get it hardly exceeds 100 actually. And as I said, platinum rhenium is the catalyst which is used in almost all these units. And I had already talked about earlier as to what is the role of rhenium here. This is the process flow diagram of a semi-regenerator reformer. You take in the feed here, and that is mixed along with the recycled gas from the compressor. And it goes through the feed furnace where it is preheated. And then it goes into the first reactor. This is where you actually do the first reaction in catalytic reforming, and then the interheater. We don't call this heater as a heater. It is called interheater because it is between these two reactors. So it goes through these heaters and the third reactor, and finally it actually goes through the cooler. In most of the units, we don't actually take this gas and cool it directly by water. We actually preheat the feed. So the feed and the recycle is preheated with this reactor effluent, so that we recover this heat, so that the furnace duty comes down. And then we separate these gases. So whatever condenses comes down, and whatever cannot condense is mainly hydrogen and some of the lighter hydrocarbons. They go up. Part of it is recycled. And here again, we try to settle down the liquids. This is like a demister, and then the gases are recompressed again. And along with the liquid, it passes into the separator where actually we take out the hydrogen. And the liquid is then actually stripped out of the fuel gas, which is C1, C2. And then, of course, this is like a naphtha stabilizer or a debutanizer where you recover the LPG. And then the reformate that is the C5 plus material is here. So I'll just go through this flow sheet once more. After the reactor, the reactor effluent we actually cool down, and we recover all the hydrogen and the lighter components, and they are compressed again along with the bottom into a separator where the hydrogen gets separated out, and the rest of it is actually stripped in order to get rid of any residual hydrogen plus C1 C2. We don't want to lose any C3 components because that is part of the LPG. And so all this is what is called as the wild naphtha or wild reformate. And that is, then fractionated in this column, very similar to the naphtha stabilizer that we discussed in the crude distillation unit. And so this is the LPG that comes out, and whatever is below is the reformate. And this is actually added directly into the gasoline pool, or actually it is used to separate out the benzene, toluene, and the aromatics and recover those components. Coming on to the CCR type of reformer, as I've mentioned several times, this is the most modern type of catalytic reformer. It is a huge step change. Actually, if you ask me, it is a disruptive technology which actually made semi-regenerative reformers almost obsolete. And after I discuss the CSI reformer, I'll tell you why semi-regenerative reformers are still around. Not because they were constructed and they are operating, but also there are other reasons why semi-regenerative reformers are still preferred. But in CSI reformer, the continuous process, it is a continuous process where the regeneration as well as the reaction is continuous. So we have to add a fourth reactor here, where the fourth reactor is actually a special reactor which actually does the regeneration, and it adds to the operating reactors. So the advantage of CCR process is against traditional methods. The advantage is that it actually helps us to produce more octane barrels. That means higher octane reformate being working in a low feed, even with a low feed quality, it can give you a higher reformate yield. These units can work continuously without a shutdown even for 5 years. The reformers that we operate in Jamnagar, I think none of these units, unless there is an emergency, there is no planned shutdown of these units. They shut it down only when they're ready to change the catalyst. Because even in these units, you have to change the catalyst because some of these impurities, which come along with the feed, even in ppb level, parts per billion level, in 5 years, they are good enough to actually, affect the catalyst activity. And so in 5 years, so typical catalyst vendors, catalyst suppliers, they guarantee a life of 5 years where the catalyst, would be same in terms of its activity. But after 4 years, you can start seeing the deterioration in the catalyst activity. And maybe around 5.5, 6 years, it's just about the time that you would like to change the new catalyst. Because after that, it becomes, you start losing money if you continue to still operate that catalyst. So you need using catalyst with less stability but higher selectivity and yield, and it requires lower recycle ratio and lower hydrogen pressure, as I told you earlier. And this is the typical diagram of a CCR reformer. There are two technologies in the market today by two different technology licensors. One of them is UOP, which is an American company located in Chicago. They are more than 100 years now in the oil industry and one of the most inventive companies in the world. In fact, if you recall, when I was giving you the introduction on catalytic reforming, the scientist in UOP invented actually catalytic reforming. So, we have to actually thank UOP for even inventing this technology right in the beginning in the early 40s. But they came up for the first time. In fact, UOP was the first company which came up with this new disruptive technology where actually you take in the feed and then this is the recycled gas that you mix from the compressor. And so the combined gas, the combined feed that goes into the feed effluent heat exchanger, where actually the reactor effluent preheats this mixed feed. And that feed then goes into the first furnace. These are the fired heaters. So this goes into the first furnace, and then actually that feed goes into the first reactor. Now, here in this particular configuration, you can see that one, two, three, four. There are four reactors stacked one above the other. So basically, the catalyst actually flows down by gravity. So there are two movements in this structure, as you can see. One is the movement of the gas or the feed, and the other is the movement of the catalyst. Okay, and they are co-current. So basically, the feed goes through the furnace, preheats, and then actually something like 510, 520. It goes into the first reactor. The volume of this first reactor is small because you don't need large amount of catalyst here. Then this gas is taken out after the first reactor and then goes into the interheater. After passing through the interheater, it goes into the second reactor. The volume of this reactor is slightly bigger than the first one, but the catalyst is still moving down. After you goes through the journey through the second reactor, then you actually withdraw the gas again, to take it through the second interheater, and put it into the third reactor. The third reactor is slightly bigger than the second reactor, and there also the catalyst is moving down. Then once the gases exit the third reactor, then you take out the gases and put it through another interheater and then pass it to the fourth reactor. And the catalyst is still moving down. And once actually it reaches the bottom, the gases, then you withdraw the gases and you put it through the feed effluent heat exchanger where actually it preheats the feed. And then you take off the heat, rest of it by a fin fan cooler or what we call as air coolers. And then the rest of it by water cooler, that is using cooling water. We call this as a trim cooler in the industry. And then you separate, this is the knockout pot. So this is the knockout drum where actually the liquid condenses out, gets dropped to the bottom. The gases go to the top, and then you have a compressor. So part of the gas is recycled here, while actually the rest of it goes into the recovery section, where you have the net hydrogen-rich gas, and then the bottom liquid goes into what we call as the stripper or the stabilizer, where you remove the fuel gas as well as the LPG. This is like an after stabilizer. And the reformate then gets removed from here. And this is where actually you have all the aromatics present, C6 and C6 plus aromatics. So this actually can go directly into the gasoline pool, or you can take it into for recovery of aromatics. Now, while at the end here, what happens differently to semi-regenerator reforming? In semi-regenerator reforming, as you can see, the catalysts were fixed here. So the catalyst just stays, the gases move, right? And after about a year, when we reach the end of run condition, then we just stop the whole unit, and there are provisions provided in each of these reactors to put air, but we put diluted air. That means the air that we put in is only about 2 to 3% oxygen level, not 21% oxygen that we breathe. So we dilute that with nitrogen. So in order to reduce it down to 2%, and that 2% oxygen is then used to burn off the carbon in a very slow manner. Why a very gentle manner? Because we don't want the catalyst to sinter or the platinum to get agglomerated on the catalyst. So, and we'll talk about regeneration in a moment. So what happens now here is that this catalyst, since it is moving down, it actually exits from the bottom and it is airlifted, or in this case, we are nitrogen, lifting it with nitrogen. So it is lifted by nitrogen to the top of this reactor. And here actually the regeneration takes place. So this is actually the catalyst regenerator, where right from the top, by the time it exits to the bottom, you get fresh catalyst. So what reaches to the top is the spent catalyst. What comes out from the bottom is the fresh catalyst, and this is then lifted along with hydrogen. Now it's no longer nitrogen or no longer air, but it is lifted now with hydrogen because this is hydrogen rich atmosphere here. So this catalyst is lifted by hydrogen to the top and the journey continues. So this is what is CCR platformer technology as actually being licensed by UOP. There's another company which is from France called Axens, and the development part by Axens is by a French institute called Institut du French du Pétrole, IFP, which is a French government-owned research organization. And a lot of technologies, in fact, IFP has been just like UOP. IFP also has been a great contributor in our industry in terms of various technologies that they have developed and commercialized. A very innovative and inventive company, and I in particular and government of India are quite indebted to IFP because they were instrumental in setting up the Indian Institute of Petroleum in Dehradun, which I headed from 2003 to 2016. So here actually you can see that this is slightly different as compared to this. Here actually this configuration is one on the top of each other. So all the reactors are like stacked reactors on the top of each other. This is called stacked configuration. You can see the title here, stacked configuration. While here this is side by side configuration. So you start off with the first reactor, then the second reactor, then the third reactor, and the fourth reactor, and then the regenerator. So the idea is the same. So you preheat the feed and bring it here, and then you get the catalyst, get the feed to go through this reactor. And similarly, of course, it is not shown here, but there is a preheater here, and then it again goes through the second reactor, and then the third reactor, and then the fourth reactor, the same journey, and then you get the reformate. While the catalyst movement is also co-current, so this catalyst actually goes and it goes and then it moves actually from this reactor to this reactor. So the catalyst moves from the first reactor. It is lifted by hydrogen to the second reactor. Then it falls into the second reactor. It moves down. Then it gets hydrogen lifted to the third reactor, falls through the third reactor, gets hydrogen lifted to the fourth reactor, then goes through the fourth reactor, and then you actually lift it with nitrogen into the regenerator. So you don't actually lift now with hydrogen because otherwise this is air-rich atmosphere. So you actually had nitrogen lifted to the regenerator, and here the regeneration takes place. And then, of course, you nitrogen lift it back again to the first reactor. So what goes into here is the spent catalyst, and what comes out is actually the and the color coding is indicating that by the time it actually comes down, it is like fresh catalyst, so it remains fresh here. It remains slightly. It starts deteriorating, and it's pretty much deteriorated here. So this diagram also by color you can see that how the catalyst gets deactivated. And one more thing which I wanted to tell you. So by the diagrams that you must have seen, you must have got a feeling that we fill up the entire catalyst. Like we fill up the entire reactor with a catalyst. That is not so. Actually, remember, we cannot afford to have high pressure drop through these reactors. So one way to fill up the catalyst in the reactor is this way, where actually you have a longitudinal flow. So you put a screen here, what we call as a Johnson screen, and then it's a very fine mesh, and on which you put the catalyst on the top of it, and you can get the gas pass through this. But these reactors are tall, and even if you have said, let's say 4 to 5 meter tall reactor, you can calculate the Argun equation, the delta P across the bed. So the delta P would be huge. And as you know that pressure has a very important role to play in this kind of chemistry. So we don't want to lose the pressure just because there is a pressure drop through the reactor. So what the industry came up with is a kind of a radial distribution of the catalyst. So the same reactor, what was done was actually the gases were allowed to flow radially through the catalyst bed. So there is a center pipe created where the center pipe is actually blocked from the top. So the gases cannot go through the center pipe as they come through. They actually go through the side. And then you have screen here on both sides, what we call a Johnson screen, and the catalyst is contained between these two screens. So the gases they pass through this catalyst bed. Now the distance through which they have to travel is less, and the distribution also becomes less. It becomes much better because now actually there's a large area through which they can pass through. So the reaction is also better. In fact, all the catalyst gets to see the entire gas. While here, actually, depending upon how you fill the catalyst, you could have, longitudinal, in other words, what can happen is that you can create channels through this reactor bed through which the gases might pass through without reaction. While here this is not possible because you have two screens between which the catalyst is filled, and the entire gas has to pass through the screen, and so it has much larger surface area on both sides. And this way, actually, the reactor volume does go up because there is a little bit of empty volume that you have to actually afford for the gases to get distributed through the screen and then the area of the center pipe. But then we get much less pressure drop for the same amount of catalyst. So this has actually remained since then. And in fact, the same configuration is used in the regenerator also. So these lines actually I copied for you. The evolution towards continuous reforming and the implementation of continuous CCR impose the radial type of low pressure drop reactor once and for all. So this has actually remained in the industry today. And the trend towards the total pressure of 3 bar has left no other choice. Because if you lose 3 bar pressure here itself, then you can't operate the unit anymore. So the reactors are built of low alloy carbon steel, which are actually the metallurgy of this reactor is chosen so that it can withstand the high pressure, the high temperature along with the hydrogen environment. But just remember this very important fact that we don't fill up the catalyst longitudinally and we don't pass the gas actually through the bed here. We actually pass the gases radially, the way it is, as you can see here, so that we have less pressure drop and the distribution is also uniform right across the bed volume. Now coming on to catalyst regeneration and the catalyst circulation. So as far as the CCR reformers are concerned, two things are very important, catalyst circulation and catalyst regeneration. So if you don't circulate the catalyst, there is no CCR reformer anymore. Then it becomes semi-regenerative reformer. So if you look at this configuration, if I don't pass this catalyst from one reactor to the second reactor to the third reactor to the fourth reactor, then this is like a semi-regenerative reformer itself. Okay, and in fact, this is how actually Accents invented this technology because they were looking at a market of semi-regenerative reformers being converted into a CCR reformer. So you can see now why these two companies actually have a different path. It's very interesting the way actually industry does research. UOP was the first to actually invent reforming, right? So there was a large body of knowledge, both in terms of science, in terms of chemistry, in terms of technology, in terms of engineering at UOP. And they use that to an advantage to come up for the first time a disruptive technology like CCR. And they come up with a stack configuration because it's easy to flow something with gravity from the top to bottom. So here actually the entire catalyst flows because of gravity. While after this technology got implemented and commercialized, Axens, thought how they can actually also commercialize a CCR kind of technology, but to be away from all the patents of UOP and to be able to, have a complete freedom to operate a CCR reformer technology. So they come up with the side-by-side configuration like this. And the market, it opened up a big market for them to convert a semi-regenerator reforming configuration to a CCR kind of a configuration. So catalyst circulation is very important. And of course, no CCR reformer is good enough until you have catalyst regeneration as well. So coming to the catalyst circulation, basically the objective is to transfer the catalyst within the loop from reaction from one reactor to the other in case of Axens technology, and from the reactor to the regenerator in both these technologies. The constraint, of course, is that when you transfer the reactor, the catalyst from the reactor to the regenerator, you're going from a hydrogen-rich atmosphere to an oxygen-rich atmosphere. So basically, you have to be very careful when you transfer the catalyst. And also the transfer of the catalyst is from a lower to a higher pressure section. Because as you go along, the pressures actually go on reducing. And also this catalyst is subject to attrition. As it keeps on passing through so much of metal, it sees, it goes through the screens, it goes through valves, it goes through so many equipment. So whenever a solid particle will hit a metal surface, it will definitely tend to, get into a powder form. So this is what we call as attrition. And that can actually plug the screens, those screens which I talked about, what we call as Johnson screens. So we have to be careful about all this when you transfer the catalyst. So in the Axens types of configuration, you can see this diagram, how the catalyst is transferred. Here we have not shown the gas flow, only the catalyst flow. So you use hydrogen to actually lift the catalyst through a standpipe. This is what we call as a standpipe into a hopper here. These are called as the upper hoppers, and so these are the hoppers in which the catalyst is stored. And this catalyst then flows down through these two lines into the reactor below. I'll come back to this, the upper section of this reactor later. So this hydrogen is used to actually transfer the catalyst to this hopper, and from here it flows into this reactor. Then it goes into a collection vessel from where actually it goes into this pot called as a lift pot. This is called as a lift pot. And from here again, it gets transferred to this the upper hopper, and the journey continues. And ultimately, when it goes into this lift pot, we don't use hydrogen anymore. We use nitrogen, and then it gets lifted to the top of this regenerator, where actually it goes through the surge drum and the lock hopper and into the regenerator. And then when it goes into the lift pot of the regenerator, then again we use nitrogen to actually lift it up to the top here. So here again, it gets deposited in a hopper. And then in case of Axens technology, there's a reduction chamber where you actually reduce the catalyst, and I'll talk about that in a moment. But this is how you actually, maintain the circulation. As you can see that there's a level controller by which actually we pass the catalyst through. So if suppose you put if you actually lift too much of catalyst, this level will come down, and therefore actually the amount of hydrogen that you put through is controlled by this level controller at the top, and same thing everywhere. So this is the typical way we circulate, and the same thing happens in UOP reactor also, only that they don't have the side-by-side configuration. There's one on the top of each other. and that the catalyst, when it comes down from the bottom, is lifted by nitrogen to the top of the regenerator, and then from the regenerator bottom by nitrogen top to the first reactor. The lift pod that you see here at the bottom, the configuration is here, where actually the catalyst comes from the lower hopper here, and then there is a kind of a funnel structure here, where this hydrogen or nitrogen, whichever it may be, depending upon whether it's a reactor to whether you're passing it into another reactor or the regenerator, the hydrogen passes through here and it actually lifts the catalyst onto the next hopper. So here, of course, this is the main gas coming through, and there is actually a split gas which has got a control valve. This is for fine tuning the flow of the catalyst. So this is how the lift pot is designed, and this is typical in the industry whenever you have to actually lift the catalyst to go. So this is actually in a fast fluidization mode. This is what we call as a fast fluidization mode or a continuous carryover mode. Coming on to the catalyst regeneration, this is actually the heart of catalytic of catalytic reforming, because unless and until you are able to regenerate the catalyst, you are not able to use this catalyst on a continuous basis. I mean, say in SR reformer, after 1 year, you have to regenerate the catalyst. While in CCR reformers, you have to regenerate the catalyst continuously, right? So what we do here is that the catalyst regeneration to recover catalytic initial properties. And basically, what we try to do is we burn off the coke on the catalyst. So the coke on the catalyst to be burnt. What happens is that during the reaction, the chloride level on the catalyst also drops. In other words, the acidity of the catalyst also drops, which is not good, because if you recall the chemistry of catalytic reforming, there are molecular transformations that happen because of the acidity on the catalyst. So that chloride level has to be readjusted. The platinum on the catalyst tends to get agglomerated because of the heat that it sees because of the hot gases. So that the metal has to be redispersed and it has to be restored. After regeneration, this is actually your nitrogen, which is blended along with air. So these gases actually contain a large amount of HCl, hydrogen chloride. It has got large amount of acid gases because of the chloride and the burning of carbon. And that carbon is not just pure carbon; it has got hydrocarbons as well. So you get water generation as well. So the water along with chlorine can form HCl. So you have to have a pretty elaborate gas treatment section to actually make sure that you don't release acid gases into the atmosphere. And finally, of course, the catalyst in that process of getting carbon burnt gets oxidized. Platinum gets into an oxidized state. So we need to reduce it down to its virgin platinum form. So we need to have a metal reduction. So we actually do it with hydrogen before going back to the reaction section. So there are 5 steps, basically 4 steps that we do in terms of catalyst regeneration. This is not just burning the carbon and you are done. Okay. So you burn off the carbon, then you adjust the chloride level, and then actually you disperse the metal back, and then you reduce the metal, the platinum oxide, back to platinum, or tin oxide back to tin. Remember, these are bimetallic catalysts. So here, this is more detail actually. I'll just walk you through this. So the catalyst burning off is performed in 2 steps. I think this you can read in peace. What I would like to explain is actually in the entire regenerator, there are 2 sections which actually are involved in burning off the coke. So there are 2 burning zones. Burning means you actually oxidize the coke into carbon dioxide and water. The coke contains both hydrocarbons and free carbon. And then once the coke gets burnt off and you have just the a carbon-free catalyst. Then you do oxychlorination. We use perchloroethane to actually be as a chloride carrier, and that actually redistributes the metal again on the catalyst. And then we actually, since the catalyst get moist because of the water formation, we dry the catalyst. So there is a calcination step, and then there's a reduction chamber where you actually reduce the platinum oxide or the tin oxide back to their virgin character like platinum or tin. So this diagram explains it all. So these are the that we talked about. And so the spent catalyst comes here, and you got air here, but this gets diluted with combustion gases, which is basically carbon dioxide, etc. So you don't actually put 21% oxygen in here. And so there's a primary burn that you actually remove almost 80% of the carbon. And then the rest of this is like a finishing section where you burn the rest of it. And then actually the catalyst comes down here into the oxychlorination section where we actually put perchloroethane to redisperse, to actually put the chlorine back into the support as well as to redisperse the platinum. And then actually it goes into the calcination step where actually the hot gases are used to dry the catalyst. And then after that, we have one more step which is not shown here, which is the reduction step, where you put hydrogen. And that is generally done at the top of the first reactor. So as you saw here, the top of the first reactor is actually the reduction chamber. So this is oxidized state catalyst which is brought here, and then you put hydrogen to reduce the catalyst, and the same thing happens in the UOP unit also. This is how it all happens, and this diagram shows the catalyst attrition. See, over a period of time, initially the catalyst is good in terms of these small balls. Here you can see the scale, and you can see that typically these balls are like 1.2, 1.2 millimeter diameter. After continuous use, if the attrition index of the catalyst is not good, it can get into these small pieces, and over a period of time it can get coked up so it becomes black. And then if you don't actually are very careful, you can even get into a powder form. And always remember that the advantage of this radial flow that I talked to you about, that also helps in one more way, and that is that the entire bed is not sitting on the screen. So the catalyst which is at the bottom can get crushed because of the head, hydrostatic head of the catalyst sitting on the top of it. Here actually the head is small, and basically the catalyst is filled up more in this way. So and actually the catalyst moves in the CCR reformer. This catalyst moves from this bed to the bed below. In semi-regenerative reformer, it's fixed actually the way it is. So this actually helps you to reduce the attrition and therefore keep the catalyst with is for a longer duration. This is a typical photograph of a CCR reformer. Actually, if you just walk in front of a CCR reformer, you will not actually notice that it is a CCR reformer, particularly the UOP type of CCR reformer, because it appears like a big column and you might actually mistake it to be a distillation column. So here you can see the CCR reformer. This is stacked configuration. And this is one unit where actually you have a lift or an elevator provided for the operator to go up, because these structures are so tall that it is physically impossible for the operator to keep on going to the top several times in a day. So here, basically, this could be like 50 to 60 or even 70-meter tall structures. And so an elevator is provided for the operator to go up. This particular steel structure that you see at the back here, This is the stabilizer. This is a distillation column. These are the furnaces that I talked about. This is the feed furnace. This is the interheaters. And this tall structure that you see at the back here, this is actually the UOP type of stacked reformer. I mean, this is of course slightly dated, but the size, the CCR reformers are now actually almost like 50% of all the reformers that operate. If you remember, I mentioned that semi-regenerative reformers still do have a place in the world. And the reason is that actually CCR reformers, as you would have noticed by now, if you are looking at the UOP type of a configuration, these are expensive. Okay, as compared to semi-regenerative reformers, this is simple and much cheaper compared to a continuous regeneration reformer. So generally, actually, if you're looking for low capacity, if suppose the refining capacity is small. So I'll give you an example. Suppose today Guwahati refinery in Assam wants to put a semi-regenerative reformer. They don't have an SR reformer as of today. But if they want to put a catalytic reformer in Gujarat in Guwahati refinery, that refinery capacity is 1 million ton per annum. So you can imagine that if you want to put a reformer, the capacity would be hardly 150 to 200,000 tons per annum. For such small capacity, the design and construction of these kinds of reformers become very difficult because the diameters will be less, the movement of the catalyst and the hydraulics, etc., is very, very challenging. So in such cases, there is no other option but to actually go with this kind of reformer, which is semi-regenerative. And that is the reason why in Numaligarh refinery, which is a 3 million ton refinery, when they decided to actually make Euro 6 gasoline or BS6 grade gasoline, they had to put a semi-regenerative reformer because their reforming capacity is around 250, around 300,000 tons per annum. So there is a break-even number, something like 400, something like 350 to 400,000 tons per annum, or zero point 0.3 to zero point 0.4 million tons per annum, above which actually CCI reformers are preferred. Below 0.35 to zero point 0.4 million tons, generally the industry prefers semi-regenerative reformer because it makes economically more viable. And that is the reason why worldwide there are only two licensors of this technology. One is Access, the other is UOP. And now, actually, since CCR reformers are the choice of the future, UOP has actually has exited the SR reformer market. So, if you are really looking for putting an SR reformer in a refinery, there's only one licensor, and that is Access. No other license. I mean, UOP doesn't offer that technology anymore. So they only offer CCR. So that is all that I had on catalytic reforming.